Welcome to This Explainer. Today we're tackling what is honestly the most thrilling, high-stakes collision in modern tech, the convergence of quantum computing and artificial intelligence. Our goal here is pretty simple. We want to demystify quantum machine learning, or QML, and prove to you that it's absolutely not just science fiction. It's actually a highly practical toolkit, and it's actively solving some of the most stubborn AI bottlenecks we face today. Okay, let's dive right into this. Think of this relationship as a massive infinity loop, a true bidirectional symbiosis. It's really crucial to understand that this is a two-way street. On one side, classical machine learning agents are actually optimizing our quantum hardware. They're busy calibrating qubits, designing error correction codes, and mitigating noise in real time. Then, on the flip side, quantum processors return the favor by accelerating AI logic. They use properties like superposition to process massive, high-dimensional datasets that would completely overwhelm even our best classical systems. So they feed into each other, creating this incredibly powerful, ongoing feedback loop. To navigate all this dense information, here is our roadmap for today. First, we'll unpack that quantum AI symbiosis. Second, we're going to see exactly how quantum systems are smashing classical data bottlenecks. Third, we'll identify the hybrid workhorses powering this whole transition. Fourth, we'll lay out the exact evolution timeline. And finally, we'll look at the ultimate end goal, quantum-native AGI. We've got a clear, logical path through these concepts leading straight to the future of intelligence. So let's get started. Section 1, the quantum AI symbiosis. To really grasp this partnership, we've got to ground ourselves in our current reality. Right now, we're operating in what physicists call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Because we don't have perfect, pure quantum computers just yet, this partnership is absolutely vital. See, because we're in this noisy era, current qubits are incredibly fragile. They experience decoherence really easily. But here's where it gets fascinating. Classical machine learning is actually a prerequisite for scaling quantum hardware. Without classical ML stepping in to drive error mitigation and real-time calibration, quantum systems just can't scale effectively, let alone reach any sort of economic value. But once AI stabilizes the hardware, the quantum side accelerates the AI. By utilizing superposition and entanglement, quantum kernels allow for way richer decision boundaries. They can separate complex data so much more effectively than classical methods ever could. And we're already seeing this in the real world today. Over in healthcare, researchers at St. Jude's and the University of Toronto are using these models to target cancer proteins that were previously considered completely undruggable. And in finance, global banks are jumping in, using quantum-enhanced models for much faster, super accurate risk assessment. Moving to Section 2, smashing classical data bottlenecks. As we push to scale AI up through its developmental layers, from basic machine learning all the way to autonomous agents, classical computing is slamming into some massive physical and energy walls. To break through those walls, we've got to jump over some very specific hurdles. If you know classical deep learning, you've probably heard of the vanishing gradient problem, where a network basically stops learning because the feedback signal just gets way too weak as it passes through the layers. Well, quantum computing has its own highly complex version of this. It's called the barren plateau. Basically, as you increase the number of qubits in a noisy system, the optimization landscape can become completely flat. The system essentially gets lost. It can't find the right answer. It's kind of like wandering around a massive, perfectly flat parking lot with absolutely no signs. Overcoming this barren plateau, mainly through better hardware-efficient circuits, is the absolute key to unlocking quantum deep learning. And honestly, beyond training hurdles, we're facing major execution bottlenecks, particularly when we talk about Layer 6 agentic AI. Autonomous agents require real-time reasoning, but the classical hurdle here is something called the combinatorial explosion. Think about it. If an AI agent tries to route global logistics, it has to consider millions of variables: traffic, weather, fuel windows, the whole shebang. The sheer volume of options completely freezes classical processors. There are just too many paths. So what's the quantum solution? Well, quantum systems naturally handle exponential search spaces. They can process these massive combinatorial problems basically instantly, which ensures our autonomous agents can make dynamic, real-time decisions without freezing up. This brings us to Section 3, hybrid workhorses. We aren't going to just magically jump from classical computing straight into flawless, pure quantum systems overnight. We're crossing a bridge. And that bridge is built entirely on hybrid algorithms that take the absolute best of classical processing and combine it with quantum heavy lifting. And this brilliantly illustrates the exact tools getting us across that bridge. Right now, we have two foundational hybrid algorithms doing the real heavy lifting. First up is VQE,
the variational quantum eigensolver. Its main job is to iteratively optimize a circuit to find the minimum energy state of a system. And this is a massive unlock for Layer 2 machine learning classification and Layer 5 generative AI. Imagine simulating molecular energy levels for rapid drug discovery. VQE is your go-to. Second, we have QAOA, the quantum approximate optimization algorithm. Remember those massive logistical problems we just talked about? This is the engine for solving them. It finds near-optimal solutions for combinatorial optimization, which makes it the absolute perfect engine for Layer 6 agentic AI pathfinding.
But algorithms are honestly nothing without the physical hardware, and the quantum hardware ecosystem is incredibly diverse. Different physical architectures actually favor completely different AI tasks, and understanding this is super helpful to see where the whole industry is heading. Take superconducting hardware, for example. Built by heavyweights like IBM and Google, these systems operate at ultra-cold temperatures and have incredibly fast gate speeds. We're talking nanoseconds. That rapid iteration makes them ideal for Layer 3 and 4 deep learning. Photonic systems, on the other hand, operate mostly at room temperature, and they integrate super easily with existing telecom networks. Because of that low latency distributed networking, they are absolutely perfect for Layer 6 agentic AI. Finally, we've got trapped ion systems. Sure, they might operate just a bit slower, but they offer exceptional stability and high fidelity. That extreme accuracy makes them incredibly relevant for Layer 7. That's the theoretical realm of artificial general intelligence, where precise reasoning is vastly more critical than raw speed. Which leads perfectly into Section 4, the evolution timeline. Think of this as our chronological journey, charting the exact path from our current hybrid commercial adoption all the way to pure native quantum systems. The transition over this next decade is mapped out with some very distinct milestones. Right now, between 2024 and 2026, we're deep in the hybrid era. Classical systems are handling the bulk of the data, while the quantum processing unit swoops in to run the really difficult mathematical subroutines. But there's a huge commercial tipping point projected right around 2025 to 2028. That's when these hybrid models will start generating massive revenue by actually outperforming classical benchmarks in optimization and pattern recognition. This pushes us right into the 2027 to 2030 window, the era of quantum utility. This is where we'll start seeing a useful quantum advantage, where complex algorithms consistently beat classical supercomputers. Finally, looking out to 2033 and beyond, we enter the era of quantum native AI. We're talking fully error-corrected, fault-tolerant systems where the AI is designed from the ground up purely for quantum logic. So, you might be wondering, what's the actual technical milestone that triggers that middle phase, the era of quantum utility? Well, the magic target number is 1,000 plus. Leaders like IBM and Google are aggressively aiming to build systems boasting anywhere from 1,000 to over 10,000 logical qubits. Once we breach that specific threshold, the sheer computational advantage over classical machines, especially in fields like high-dimensional data processing, is going to become absolutely undeniable. And the reward for reaching the end of this timeline? It's literally monumental. $2.7 trillion. That's the projected economic value waiting for us in the 2035 plus window. This is the financial impact of finally achieving large-scale, fault-tolerant quantum-native models that can host end-to-end AI reasoning, completely without relying on classical assistance. Finally, Section 5, Quantum-Native AGI. This is the ultimate destination, the absolute peak of the AI developmental mountain. We're talking about Layer 7, Artificial General Intelligence. To really get this, we actually have to reframe the entire AGI conversation around one thing: energy. The ultimate stakes here are overwhelmingly physical. See, trying to achieve true AGI on our current classical silicon architecture would theoretically require data centers that consume the power of a small city. You'd practically melt the grid just trying to run a single reasoning model. We're rapidly approaching a hard wall defined by raw wattage and transistor counts. The quantum solution? It completely bypasses those massive wattage limits. Quantum machine learning offers a path where intelligence actually scales based on qubit quality rather than sheer electrical power. And the goal of these quantum-native architectures isn't just to build a slightly better chatbot that predicts the next word in a sentence. No. By leveraging quantum interference and superposition, the system moves closer to real human-like reasoning. It allows the AI to actually understand the underlying reality of the data at quantum speed. It is a completely different paradigm of intelligence. So I want to leave you with a final provocative thought to really tie all this together. Is true artificial general intelligence even possible without quantum-native systems? When you sit down and look at the physical energy limits of silicon, and you consider the freezing effects of that combinatorial explosion in classical systems, we really have to ask ourselves, is quantum computing just an optional speed boost, or is it the mandatory physical prerequisite for the ultimate layers of AI? Thank you so much for joining me on this explainer as we explored the quantum frontier. Keep questioning the limits of what's possible.